Okay, so in a lot of ways, we're going to talk today about ideas that you guys have already talked about in Chapter 3. So we're going to be talking about constant rate of change. We're going to be talking about dy's and dx's, but we're actually working on Chapter 4 stuff. So we're starting Chapter 4 and those kinds of ideas. So you guys have talked about dx before, but we're going to be a little bit more specific with how we talk about dx today. Okay. So up until this point, we treated delta x and dx kind of the same. We said both of them represent a change in x. But now we want to be a little bit more specific with the differences between the two of them. So now we want to talk about dx as being a little change in x. Okay, so we want you to kind of think of delta x as being a little bit larger and dx as being smaller. There's also going to be some other differences in dx and delta x. You guys have talked about parameters, constants, and variables now. We want to think about dx as being a variable, whereas we're going to think about delta x as being a parameter. Okay, so delta x is going to be this unknown constant or in some cases a known constant, and then dx we're going to think of it as varying. Okay, and dx you also want to think about as being a little change in x. Well, how little is little enough? It depends on what situation that you're going to be in. So in some situations, little may mean different than in other situations. So we're going to talk about, well, how small is small enough? How do we decide that we have a small enough dx? We're also going to call this dx a differential. So this is kind of a fancy calculus word. So if you talk to mathematicians, they're going to call dx a differential. All right, any questions? All right, now we're also going to be talking about dy's and dx's in the specific situation of constant rate of change. So the reason that we talk about dy's and dx's is because you guys have talked about when we have constant rate of change, we know that dy is always a certain amount of times larger than dx. So we're going to be using dy and dx in similar situations where we're assuming that we have a constant rate of change. Okay, so because we're talking about constant rate of change, dy is going to be a multiple of dx. Okay. Now I've got a little video to show you guys. All right, so yeah, so this is an older one. So this is an older Olympics. So this was not this past summer. This was a while ago. When he first, I think it was the first time he broke the world record. Okay, but I'm sure some of you guys watched Usain Bolt run this summer. So we're going to talk about him running this 100-meter dash, okay, or this 100-meter sprint. So in this particular case, in this race, he ran 100 meters in 9.58 seconds. Okay, so that's pretty fast, right? 100 meters in 9.58 seconds. I know you're wondering if he's even human. They say that he is, but I wonder sometimes. Okay, now, what I want you guys to figure out for me is how fast he ran in miles per hour. So I want you to put your Chapter 1 hats on, okay, and see if you can do this conversion for me. Now, you're going to need a little bit of information, okay, so I'm going to give you guys a couple pieces of information that may come in handy if you don't remember the conversions. Okay, so we know that 3.28 feet is the same thing as 1 meter. So that may come in handy. And we also know that there are 5,280 feet in a mile. I have not perfected writing with this thing, so Professor Bonnie's way better at this than me. Okay? All right? So 3.28 feet in a meter, and there are 5,280 feet in 1 mile. Okay? So you guys try it out. See if you guys can use this information to tell me about how fast he's running in miles per hour. Give it a shot. Working hard, that's what I like to see. Taking good notes. So there's 5,280 feet in 1 mile. In a meter. Yes. Mm-hmm. Okay, does anybody have a final answer yet? Yes. 124? Oh, 2.4. What? 224? Do you keep changing your mind, or can I just not hear you? I just can't hear you. Okay. All right, so we should have gotten about 23.3 or 23.4 miles per hour. Okay, so let's break this down. Okay, so what do we have first here? What is this 100 divided by 9.58? That's the meters per second. Perfect. When I multiply that by 3.28, what does that give me? Meters per second. Do you guys agree? Feet per second, because it's turning it into feet. Okay, so that's going to give me feet per second. And then I divide by the 5,280. What's that going to give me? Miles per second. And then multiplying by these guys changes it into miles per hour. Perfect. Okay, so that means he ran about 23.34 miles per hour. That's kind of crazy. It's like how fast a car drives.
That was only over a short distance.
That was over a short distance. You're correct. Now, my question for you, did he run that speed the entire 100 meters of that race?
No.
No. Okay, so why not? So Justin, why did he not run that speed for the whole race?
Well, because he started at a stop, so he had to sort of build up into the speed.
Yeah, so he said, he didn't start out running that fast. He had to get some acceleration going, and then he got up to a certain speed later. So at certain points of the race, he was running faster than others. So when we say that he's running 23 miles per hour, what do we really mean? Okay, so let's think about that. So at 1 second, which is what I have in this picture, so after 1 second, somebody took this picture, and he was running 13.754 miles per hour. Okay, so at this moment, he was running a different speed. What do we mean by that?
His speed increased later in the race.
So we know his speed increased later in the race, yes. What do I mean in this moment when I say that he ran 13 miles an hour?
At that point, at that 1 second interval, he was going 13 miles, 13.5 miles per hour.
Okay, so within some kind of interval, he's running 13.754 miles per hour. Did he run 13 miles in 1 second?
No.
No, so why are we talking about hours in an instant? Okay, so it's a speed, but how do we explain that to somebody that he didn't run 13 miles in an hour, but we're using this for that small interval of time? Okay, so let's think about that for a second. Okay, so here's the instant when Usain, 1 second had passed and Usain is in the race. How fast is he running at this particular time? Whoa, how did you guys see that? It looks to me like he's not running at all. So after 1 second, how fast is he running?
Not very fast.
Okay, at 1 second, if I really talk about that one instant, is he moving?
No.
No, okay? So in chapter 4, it's going to talk about, well, to have movement, we have to actually move. Yeah. So that means when we take pictures, often when you take a picture, your shutter speed is going to leave a blur when you look at your picture. So it shows us kind of where we've been and where we are now. So we have to think about the moment around that 1 second that we care about. So we have to think about, well, a little bit before and a little bit after that 1 second, what was going on so that we can figure out his speed. Okay? When we talk about constant rate of change, what two things make up constant rate of change? Change in y and change in x. Good, Deja. Okay? So if I have a change in y and a change in x, okay, and I compare those two, then we're talking about a constant rate of change. We're saying how much larger is the change in y than the change in x. Can I talk about constant rate of change without a change in y or a change in x? No, it wouldn't make any sense, right? Okay, so we're going to change how we word this just a little bit. So we're going to talk about the moment around this 1 second. So we're going to say, here's Usain at the moment when 1 second has elapsed in the race. So the moment's going to tell us, okay, we're going to consider some movement around that 1 second, and we're going to figure out roughly how fast he's running in that very, very small increment of time. Okay? So we're going to use this definition of a moment. So we're going to talk about a moment being a small change in an independent variable. So in this particular case, we're talking about seconds and meters. So which one is the independent variable? Second. So if I talk about a small change in the independent variable here, I'm talking about a small change in seconds. Okay? So we're talking about, okay, we're going to find some really small window that includes 1 second and talk about that moment. Now, when I talk about dx, the differential, that's not the same thing as a moment, okay? Remember I said a moment I'm going to set a certain way, and then dx is going to be a variable within that moment, okay? So dx is going to be varying, but the moment is going to be set. So we're going to take a look at that in just a little bit too. Okay, so your moment is going to be set to be a small change in your independent variable, and then within that moment, we're going to talk about other small changes that vary, and we're going to call those dx. Everybody good so far?
Could you stay on this side for just a small?
I'll stay on here for 5 more seconds. 4, 3, 2, 1. Remember, this is recorded, and you can watch it online, too, if you miss something, okay? You're welcome. Okay, so we're going to talk about moments where there's a constant rate of change, okay? So in order for us to talk about miles per hour, we want to think about a constant rate. We're assuming that he's running at a constant rate. So if we talked about 13.754 miles per hour, we're assuming that he's running at a constant rate. That, well, if he kept going at that same speed, he would be able to cover 13.75 miles in an hour, okay? So we have to think about zooming in on that moment so that we can figure out that constant rate of change just for that small interval of time. Okay, so let's take a look at GC for a second. So what I've got here is a graph of Usain's distance compared to the number of seconds that have elapsed. Okay, so I have a function definition that relates those two quantities. Now, I want to think about the moment in question. So what did we say? What instant do we care about?
X or T for 1.
Right, we care about 1 second. So I'm going to have to think about figuring out how to really focus in on that 1 second. So I'm going to have to zoom in a little bit to see what's going on in that 1 second. Now, the way that you guys are going to do that, all you have to do in GC is hit Shift, and then a little box is going to show up, and then you can use that box around the part that you care about. Okay, so I just hit Shift, held it down, and then created this box, and then it zooms in for me. You can, it's okay to go, oh, it's really cool, right? Okay, all right, now, in this particular moment that I've chosen, does this guy look like an essential constant rate of change to you guys? No, it's still kind of curvy, right? Okay, so it's not quite constant. So what do we need to do to try to make it more constant?
Zoom in more.
Yeah, let's zoom in some more. So I'm going to hit Shift, and I'm going to zoom in a little more. You guys are going to get to do this in your homework, you lucky dogs. Do you want me to keep zooming, or is it constant enough for you? It looks pretty good. It looks pretty straight, right? Okay, so once you zoom in enough and you find something that we would say is essentially linear, we know it isn't exactly linear, but we would say this is close enough, right? So once we have something that looks essentially linear, we're going to say, okay, I've found the moment that I like. Okay, your moment may be slightly different than your friend's moment as to how large it is, but they're going to be both small and both pretty close to one another. Okay, so here, my moment would go from 0.82 seconds all the way to 1.18 seconds. So you want to think about moments as being this interval or your window of time that you're looking at where things are approximately linear. Okay? Okay, so now back to our situation with Usain. Okay, so let's consider this particular moment that someone else has created. Okay, so somebody else went, in their moment, they zoomed in from 0.99 to 1.01. So their moment goes from 0.99 to 1.01. Okay. Now, what would I call this arrow here at the bottom? What does this arrow at the bottom represent? The change in X, okay? And then what would this arrow here represent? Change in Y, right? Okay, so notice that those changes are varying within this moment. Okay, so dx is this guy here that's changing within the moment. dy is another change that's varying within the moment. Okay, now we have to decide which static dx and which static dy we want to pick. Okay, so we're kind of telling you which one to pick in this particular problem. So it says that we know we care about 1 second, and we want to consider the moment from 0.99 to 1.01. Now we're imagining x increasing from 1 second to 1.006 seconds. So we're really focusing our attention from here to where it stops here. So we're going to consider this total amount of time, this 0.006 seconds. And during those 0.006 seconds, his distance from the start changes from 3.48 meters to 3.52 meters, roughly. Okay? Now, we want to use this information in this little piece of our moment in order to estimate his constant rate of change, his essential constant rate of change during this moment. So we know that no matter what dx or what dy that we picked within this moment, we would get close answers to one another, that our dy should be a certain amount of times larger than our dx roughly throughout this whole moment. Okay, so what we're going to do, we're going to break it down just a little bit. Okay, so I'm going to try to move this to the end of the animation. Okay, let's break it down. So we want to find these little pieces first before we find the rate of change at the moment. So what I've got going on here, I want you guys to find values, actual numbers, and then also the symbols that are attached. We're going to do a couple together, and then I'm going to let you guys work on the rest, okay? So the first one says, let's find the initial value of the independent variable. Okay, so what do you guys think the initial value of the independent variable is?
0.99.
Okay, so I heard 0.99, I heard 1, and I heard 1.01. Okay, 0.99 to 1.01 is the moment, but that's not where we're starting to consider our change. Where are we starting to consider our dx here?
1.
1. We're starting that at 1. Okay, so we want to make sure that our initial value here, we want that to be 1. Why is it not writing? Very strange. There we go. Okay, all right, so the initial value is 1. Now, what symbol could I use for that 1?
X.
X initial would be final, yes. Okay, so let's try X initial, or X sub I is fine as well. Okay, so X initial should work. Okay. Now, what's the corresponding dependent variable there at the beginning? Okay, so now f of x would represent any x values. Okay, so the value is going to be 3.4882, which they gave us here. So that's where we're starting out meter-wise. And if we look on the graph and trace it over, yep, it looks like it's about at 3.4. Okay, so our initial value here for our dependent is 3.4882. Okay, and what can we call that? What symbol are we going to use? Okay, can we use function notation? F of 1, excellent. Using those chapter 3 skills, love it. Not going away. All right, okay, you guys try the rest. So see if you can figure out what the differential in x is going to be. The differential in f is another way of saying differential in y. Okay, so it's the same thing as dy. It's just another kind of notational common occurrence that you're going to see in math textbooks. Okay, so df, dy mean the same thing. Okay, I want you to calculate the moment. I'll go ahead and tell you there is not a symbol for the moment. So you can just put none for the symbol on that one. And then I want you guys to calculate the rate of change at the moment as well. Okay? All right, give it a try. Ben and I will be walking around to see how you're doing. Trying it yourself is how you learn. Just saying. Remember, the moment is the interval of time. Like, it's like your window at the bottom. So from here to here. Yeah, from 0.99 to 1.01. Yeah. Okay, let's see how it's going. Okie doke. So your differential in x is going to be the dx that we've chosen to look at. So we could have looked at a lot of dx's, but we wanted to look from 1 to 1.006. So how long is that dx there in that case? 0.006. Gale for the win. Okay, and that's going to be in seconds. I should have also put that this was in meters, and this is in seconds. Okay, so 0.006 seconds. What symbol could I use to represent that guy? dx. All right, now what's my differential in F? 0.0369. Let's see if I got the same answer as you. I did, yes. And that's going to be a difference in meters. And instead of calling it dy, we're going to call it df because of the convention kind of that's here. Okay, so you could write dy here, and I wouldn't be all that upset. But we're going to call it df to be consistent. Okay. All right. Now, what's the moment in question, Richard? I think you figured this out. So, what's the moment in question?
From 0.99 to 1.01.
Yep. So from 0.99 to 1. This is a delicate process. You're going to be thankful to have Professor Bonnie back who can actually write. Okay, let's try this. Okay, 1.01. All right, victory. Okay, and I have nothing symbol-wise to tell you there. Okay, so you can put NA, not applicable. Okay, that is your moment in question. How do we figure out the rate of change in this moment? Okay, one of Ben's people, help me out. Yeah, change in y over change in x. Now in this case, we're calling the change of y df. So I'm going to say df over dx. And how do we compute that? It's simple. We already have it, right? There's df, there's dx. So we just compare the two of them. So we're seeing how many times larger is this guy from this guy right here. Okay, so 0.0369 divided by 0.0065 should give us something like 6.13 meters per second. Okay, so somebody explain to me, what does that 6.13 meters per second mean? Okay, can we be more specific besides the fact that it is a constant rate of change? Okay, so this is the constant rate of change within the moment, so just within this small interval, okay? And what does that mean about dy and dx within that moment, Mayor? You can do it. Give it a shot. What does that mean about dy and dx? Okay, we know that constant rate of change and slope are the same, but what does slope tell us about this df and this dx here? They're proportional, so no matter what df or what dx I pick, I would expect that the df is how many times larger than dx? Yeah, so I'm going to expect that your df's are always about 6 times larger than your dx's, okay, within this moment. All right, we good so far? Yes?
I did the division in 6.15.
Okay, so it's just a rounding issue. So depending on where I stopped my rounding up here and all that kind of stuff could make a difference in what we ended up with. But we both got about 6.1, so I think we're okay. All right? Everybody good? All right, we're going to try one more where I give you a little bit different information. Okay, so same situation. You've got a different moment, and you've got some different information here. Okay, so we're going to start at 0.4 seconds. So that's going to be your initial x that we want to consider. And then I want you to consider stopping it at 0.408. Okay, so we're imagining dx varying, but let's think about, well, what if I paused it at 0.408 and considered this to be like my x final? Whoa! Whoopsies. Everything's still okay. The world is not going to end. So this is like your x final. Okay? All right, so see if you can still fill out the same chart, this time with this particular information. I just couldn't get it to be a sum. But yeah, so that's like your, so the 0.408 is like the final value. Still want you to find all the same things that you did before. You can now talk. The silence is dead. Okay, so where are we starting off? We're starting off at 0.4, yeah. Mm-hmm. Okay, so 0.702 is not a change. If you're finding dy dx, you need to have a change in y. That's like an additional.
That's a y value.
No. 0.702, see, that's the value that's associated, the y value that's associated with 0.4. You see that? So that's like your initial y value. That's not a change in y. That's not the difference from the start to the end.
It would be.
Okay, so notice, so the 0.702 is associated with this, and then you're going to stop it about right there. Okay, so then, yeah, so now you're going to stop it because it's 0.408, remember? It's where you're stopping. And then you're trying to figure out, well, what's the y value that goes with this guy? That's what this is asking. His final distance at that particular instant. Okay? Okay, so let's stop where we are so we can make sure we get through in time. Okay, so the initial value of the independent variable. So within this moment, where are we starting our seconds out at? 0.4. Okay, and then symbolically, what are we going to call it?
X.
X, which X? Xi, yeah. Okay. Now, the initial value of the dependent variable. So we know that our X initial is right here at 0.4. And then if I look over here, that's going to tell me about where my associated Y value is, okay? Which they already told me was what value? Excellent. So that should be about 0.702. and that's going to be in meters. Okay, and instead of y initial, what am I going to call this with function notation? Okay, now x would represent all the x values. Do we want all the x values? Just 0.4, yeah. So f of 0.4 is that 0.702. Okay, now my differential in x that I'm considering, the static one here, I'm considering it to be how long?
It's 0.008.
Yeah, so from 0.4 to 0.408 is 0.008 seconds. Yes, beautiful. Okay, and I'm going to call that guy dx. Differential in f, I'm going to call df. And about how long was that? What'd you get? 0.5.8? 5.4. Okay, so how are we going to get df? That's a great question. Dx times the speed. Okay, so remember from chapter 3, we learned that dy is always what relationship with dx? mdx. It's always the same amount of times larger than dx when we have a constant rate of change. Well, we know within this moment, because we're essentially linear, that dy is always going to be a certain number of times larger than dx. Okay? Now, they actually went ahead and told us how many times larger dy is than dx. What did they tell us? Yeah. So if this is his rate of change, what that means is that each of your dy's is about 3 times larger than your change in x. So this is going to be 3.04. And then my dx I already have 0.008. So when I multiply those guys together, I should get 0.0243. That I can agree with. Okay, and that's a change in meters. Okay, now my moment in question, they didn't tell us what the moment was, but I'm just going to kind of eyeball from the window about how big that moment is. We may have slightly different answers here, and that's okay. So about what did you guys say the moment went from and to?
0.395 to 0.42.
I'm good with that. You guys agree with that? Yeah, so that's roughly the window that we're looking in. To 0.42, yep. And we don't have a special symbol for that, so I'm going to leave that part off. Now, the rate of change at this moment, this should be super easy. What's the rate of change in this moment?
3.04.
Excellent, yeah. So they already told us what the rate of change was. It's 3.04 meters per second in this moment. How can I represent that symbolically? Oh, that's a good one. So I can use m. Okay, what else could I use? dy dx, but instead of dy here, what have I been using? df, yeah. df over dx. Writing on this thing is so much harder than it looks. You should give Professor Bonnie a writing award on Monday, just saying. Okay. Last and final hardest question. But you can totally handle it. I know you can. All right, we're trying to figure out his final distance from the start. Now, when I say final distance, I mean his distance at this particular instance. Okay, so we wanted to stop it at 0.408. So I'm trying to figure out, well, what's his associated distance that goes with that particular amount of time? This is the straightest I can draw. That's really sad. Let's try that again. Sometimes I feel like my job is just to entertain you.
That's an important job.
Not really. I know, it's true. I do not make a lot of money doing this. Okay, so straight across, that's a little bit better. Okay, so we're trying to figure out, well, what time is this? Okay, so we're trying to figure out if I start here at 0.702, how can I figure out where I am here? Yeah. Brock. Yeah.
And the y to dy.
Yeah. So I'm just going to add this dy to this y initial here. So that y initial I know is 0.702. Now what's my dy? Yeah, it's the same thing as df, 0.0243, which we found from mdx. So up here we already found the dy. Okay, so then if we get a final value, it should be something along the lines of 0.72.
0.7263.
Excellent. And that's going to be meters. So I've got this many meters final at that particular instance. Okay, and then I'm going to represent this with yf to represent y final. Okay, using function notation, I could also say that this is f of 0.408. Okay, that makes sense? Yes, ma'am.
Why is it not F final? Or talking in context of F?
Oh, that's a good point. So yeah, because we haven't used y so far, you're right. It probably isn't the best to use that. So how about if we just erase that? So let's just stick with the function notation then. So since our function name is f, we'll just stick with the function notation. Is that good? Okay. Any other questions? Okay, so in summary, we are finding rate of change at a moment, okay? So we first have to figure out a moment, and what are we looking for within that moment? Okay, but when I'm looking for moments, how far do I zoom in? Until it's approximately linear and I have an approximate constant rate of change. When I have a constant rate of change, we know how to deal with it, right? We compare dy and dx in order to find that essential constant rate of change around the instant that we care about. Okay? All right, you guys have a great weekend. I will see you on Monday. She is assigning a reading, so you're not going to have to turn in anything on Monday, but you will have... Yeah. Yeah. Thanks, you too.